Okay, so in this scenario, as a reminder, there's no friction here or there. All right, so there's no friction between the blocks and the ramps. However, there is friction here, and there is not friction there. And it might seem a little bit weird, but what this means, if there's no friction here, this ramp is actually going to get pushed backwards. All right, so just to think about why that happens, if we zoom in a little bit, remember this block has a normal force this way from the ramp, and it has a gravitational force this way. And if we think about the ramp itself, right, it is going to feel a reaction force from this normal force, right? In other words, because the block is feeling a force up and to the right from the ramp, that ramp will feel a force down and to the left. And these forces are going to be equal. And because that normal force has a component in that direction, this ramp is actually going to get pushed in this direction. It's going to move that way as the block moves this way. So that might be a little hard to wrap your head around at first, but that's what's going on in this question. And here, right here, there is friction, so that ramp isn't going to move. Or if it does move, it's not going to move as much. I think it's easier to just kind of intuit it that it's not going to move. But even if it does move, the answer doesn't actually change. Okay, so let's think about it this way. The center of mass of the block ramp system on the left is, maybe about right there. Maybe about right there. However, because there is no friction between the ramp and the bottom of the table, there's not going to be any external force on the block and ramp in the left or right direction. Right? There is gravitational force which pulls the block down, but there's no friction, and because there's no friction, there can be no, right, there can be no left/right external force. So what that means is the block is going to move to the right, the ramp is going to move to the left, and the center of mass is not going to move to the left or the right. It's going to stay in the same place because there is no external force. So the center of mass is not going to move left or right. But in this situation, there is external force. So here, there's friction, which means the block can't move to the left. So as this moves down, the ramp will want to move to the left, but it won't because there's friction that acts this way, right? There's a friction force that way that holds the ramp and keeps it from sliding to the left. So in this situation on the right, well, we could say something like F pushes ramp to the right, so external force acts on the system to the right, and the center of mass goes right. Right, and it's easy to see why the center of mass will move to the right, because if you think about it, right, if the center of mass is like here to begin with, and the block ends up down here, well, there's clearly more of the system's mass is to the right of that point now. So the center of mass point is going to be right further over that way, assuming the ramp doesn't move, right? Or maybe it does move, but it won't move as much as it did in this situation because of the friction force that can act on it to the right. So in scenario A, the center of mass doesn't move left or right. It actually moves down, and that's because gravity is an external force down. You didn't have to talk about that because I didn't ask about up or down motion. But there's no external forces to the left or right here. So the center of mass doesn't move. The ramp goes left, the block goes right. Here, there's friction, and the center of mass point moves to the right, because the ramp doesn't move, but the block moves to the right. So that's kind of the gist of part A of this question. Okay, so for part B, which scenario does the block have greater speed upon reaching the bottom of the ramp? So this is asking, in which scenario is the block going to be going faster when it gets down to this point here? Well, there's a few kind of key things that I was looking for here. So the first was that the initial energies of both systems, right, of both block ramp systems, right, of the block ramp system, initial energy of the block ramp systems are the same. Right, and that's because they're exactly the same configuration, right? The block is the same height above the tabletop there. However, right, in scenario B, when the block reaches the bottom, right, when the block reaches the bottom, the block is the only thing moving. But in scenario A, when the block reaches the bottom, oh gosh, right, when the block reaches the, oh, come on, I'm so bad at this. And I don't really like my, let's just use the tool. Haha. Okay, so in scenario B, when the block reaches the bottom, it's moving this way. And in scenario A, when the block reaches the bottom, it's moving this way, but the ramp is also moving. So what that means here is that in scenario B, that initial energy, which was really just gravitational potential energy of the block and Earth together, right? This is all going to be transformed into kinetic energy of the block. But in scenario A, that initial gravitational potential energy is going to turn into kinetic energy of the block and kinetic energy of the ramp. So what this means is that the K of the block in scenario A is going to be less than K of the block in scenario B, right? So all of that initial potential energy in the system goes into the block in B, but only some of it goes into the block in A. So for that reason, the block is going slower in scenario A. So I was looking for a statement about how really the energy of the systems are the same at the beginning, but at the end, the energy has to be shared between the block and the ramp here. But in scenario B, all of that energy is in the block. So therefore, the block in scenario B will have greater speed. So those are kind of all of the key things that I was looking for here.